Hello friends, welcome to this session. As far as we know, humans have always been interested in the motion of objects in the sky. Newton's idea was that gravity was a universal force acting between any two objects. From this Newton reasoned that the strength of the gravitational force is not constant. In fact, the magnitude of the force is inversely proportional to the square of the distance between the objects. In the solar system or universe, every particles attract with another particles. That's why the planets are bounded to the sun. Today we are going to learn Newton's law of gravitation and Kepler's laws of planetary motion. Every object with mass attracts with every other object with mass. Newton's realized that the force of attraction between two massive objects first increases as the mass of the object increases, decreases as the distance between the object increases. The universal gravitational constant is the inverse square law. If the distance doubles, the force drops to 1 by 4th. If the distance triples, the force drops 1 by 9. As per the Newton's law of gravitation, or we already studied in previous class, the effects of gravity through the consideration of the gravitational acceleration on Earth G and the associated potential gravitational energy. We now broaden our study and consider gravitation in more general manner through the law of gravitation given by Newton in 1687. As per the Newton's law of gravitation, every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of the masses of the particles and inversely proportional to the square of the distance between them. Here, the m1 is the mass of an object, m2 is the another mass of an object. They are apart from with a distance d. So there is a force of attraction between setup, and as per our first slide, there is a force of attraction between the two objects with their masses. This force of attraction is equal to the gravitation set up between the two objects. So this force of attraction is equal to the gravitational constant into product of the two masses having m1 and m2 respectively over the d square. D is the distance. So we can say that this force is directly proportional to the product of their masses and inversely proportional to the square of distance between them. If the force F is the force of attraction between two particles having masses m1 and m2 respectively at a distance d apart, then according to the law, F is directly proportional to the product of their masses m1 and m2 and inversely proportional to the distance square between them. So this proportionality constant is referred as the G, and this capital G is a universal constant called the gravitational constant. So we can write F is equal to G into m1 m2 divided by d square. If the m1 is equal to m2 is equal to 1 and d is equal to 1, then we can write F is equal to G. The dimension of universal constant, the universal gravitational constant is m raised to minus 1, L raised to 3, T raised to minus 2. The force being directed along the line joining the particles. Cavendish measurement resulted by experiment in an experimentally determined value of G is 6.75 into 10 to the power minus 11 Newton meter square per kg square. Today the currently accepted value is 6.67259 into 10 to the power minus 11 Newton meter square per kg square. This is the example of Newton's law of gravitation. The moon is bounded with the earth by the force of attraction, that is the G. So that the moon is revolving around the earth by a force of attraction. In the early 1600s century, Johannes Kepler proposed the three laws of planetary motion. Kepler determined that a planet moves faster when near the sun and slower when far from the sun. And Kepler was able to summarize the carefully collected data of his mentor Tycho Brahe with the three statements that describe the motion of planets in a sun-centered solar system. Kepler's efforts to explain the underlying reason for such motions are no longer accepted. Nonetheless, the actual laws themselves are still considered an accurate description of the motion of planet and any satellite. Kepler's laws provided a complete kinematical description of planetary motion. Kepler gives three laws of planetary motion and described as follows. The first law, the laws of elliptical orbits or the laws of ellipse. Second, the laws of equal areas. And third, the law of harmonics or the laws of period. According to the laws of elliptical orbits, the path of the planet about the sun is elliptical in shape, with the center of the sun being located at one of the foci. Foci is nothing but the focus, or the focus is nothing but the two other points are known as the foci of the ellipse. According to Kepler's second laws, that is the laws of equal areas, an imaginary line drawn from the center of the sun to the center of the planet, that is called as a radius vector, drawn from the sun to the planet, will set out equal areas in equal interval of times, and that is the aerial velocity of radius vector is constant. According to third law of Kepler's laws, third Kepler's law, the square of the period of the revolution of the planet around the sun is proportional to the cube of semi-major axis of the ellipse. Now I am giving the slide that describing these three laws by animation. The planet revolving around the sun in elliptical orbit, and the sun is at foci. So here one more thing is that observe carefully. This is, suppose we are taking the two section, and this section, when the planet is close to the sun, it moves faster, and when the planets are away from or farthest position, then slower. So the motion, when it is comes to the close to the sun, the planets are moving fastly, and when it is farthest at the position, then planets are slowly in motion. According to the second law of equal areas, or the here the imaginary line swept out drawn from sun to the planet. So this area, this area, this area, this area is nothing but the areal velocity, and that areal velocity of radius vector remains constant for every swept out area, and that remains constant. That value is the r square d theta by dt. And according to laws of period, here the planets of the revolution of the planet around the sun is proportional to the cube of semi-major axis of the ellipse. Now we are describing all the three laws in mathematical form. As we know, a planet P moving an elliptical orbit around the sun being at one of the foci, that is referred as S, of the ellipse. P is the initial position of the planet at any time t, capital D. And second, we are considering the second position, that is the Q, at the time, that is t plus dt. Then t and t plus dt are the point between the two P and Q, and the vector line drawn from sun to the planet P position and Q position, in the area swept out by the radius vector, that is the SP, in time dt is equal to the area of SPQ. So the area swept out is equal to half SP into PQ. Here SP is the R and PQ is the R. So we can write R d theta. PQ is the R d theta, though making an angle between from sun to the planet. So from point P to Q position. So we get half r square d theta. The area swept out half r square d theta. According to Kepler's second law, this must be constant. Let it be equal to h by 2. So this term r square d theta by dt is equal to h. So we get h by 2. Now, according to laws of period, there are 2 points A and B, and that describing the semi-major and semi-minor axis of the ellipse or elliptical orbit of the planet. The periodic time t of the planet, that is the time for one revolution around the sun, is given by t is equal to area of the ellipse and areal velocity. That areal velocity gives the t is equal to pi AB divided by half r square d theta by dt. According to Kepler's second law, this must be constant. Which term? This r square d theta by dt must be constant. Let it be equal to h by 2. Then the planet is moving in curved path. Hence it is obvious from Newton's first law of motion that force is acting upon it along the radius vector ps. Consequently, an acceleration is acting on the planet in the direction of the force, resolving this acceleration into its two components, along and perpendicular to the radius vector. So I am giving you the component of F along the radius vector, that is the radial acceleration of the planet. and that radial acceleration is referred as the function of that function is equal to d2r by dt square minus r d theta by dt square. Second term, that is the component of perpendicular to the radius vector, that is the transverse acceleration. So we can write 1 by r is equal to d by dt into r square d theta by dt. So with the help of all these three laws, so t is equal to 2 pi ab by h. Then t square is equal to, just we are squaring the both sides, so t square is equal to 4 pi square a square b square over h square. But here b square by a is equal to L, that is this L is the semilatus rectum of the ellipse. So we can write t square is equal to 4 pi square L into h square over h square into a cube. So this term is a constant, and therefore that is referred as a k for every planets, and that constant is proportional constant. So we can say that the square of the planet is directly proportional to the cube of semi-major axis A. So this is the Kepler's three laws and simple brief description of the laws. So thank you for watching the video. If you have any comments or any queries, please put it on Google Classrooms, so I will solve it. Thank you very much.